Stripping down science. The Naked Scientists.
Steel is everywhere. As one of the most versatile metals, we use it in everything from bridges and buildings to bicycles and bracelets. But how can we make it even better? I'm Ben Valsler, it's Sunday the 8th of July, and today we'll hear the story of Super Bainite, a super strong steel. We'll hear how this new wonder material is great for a range of properties, including the bearings in wind turbines, and solving the age-old problem of making good armour.
The other thing I always find quite intimidating about armour is you're up against Leonardo da Vinci, because he invented the bullet. Now, in terms of opposition, a Da Vinci design is not easy to defeat. You'd be dead 500 years and still causing trouble.
That's all coming up, along with news of a new nanotechnological way to bust blood clots, and of course, a look at the Higgs boson.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
Steel is an enormously versatile metal, and centuries of trial and error bucket chemistry has given us a wide range of steel alloys that are capable of performing almost every task that we set. So it might surprise you to hear that steel can still surprise us with previously unthought of properties. Here to tell us more about a new variety of steel, super strong Super Bainite, is Professor Harry Badishia, who invented Super Bainite at Cambridge University. Harry, thank you ever so much for joining us.
It's my pleasure.
So tell us, what's so special about this new type of steel?
Well, most steels are crystalline in nature, so if you look at them in a microscope, you'll find very fine crystals, usually of the order of a millionth of a meter in size. Now, the finer you make these crystals, the stronger the material becomes and also tougher. So toughness is the ability of the material to absorb energy when you hit it, otherwise the material is not safe when something impacts against it. So the idea here was to make the crystals so incredibly fine that they are actually finer than carbon nanotubes. So that's talking about a tenth of a billionth of a meter in size.
And how do you actually do that? How do you go about controlling the size of these crystals?
Yeah. So we discovered that if we grow the crystals inside the solid steel at a low enough temperature, then they will grow extremely fine. So in this case, we are heat treating the steel at the same temperature at which you would cook pizza. Yeah. The only catch is that we require to hold the steel at 200 degrees centigrade for 10 days. So it's a very long cooking process, around 200 degrees centigrade.
And is it all about that heat treatment, or are you adding extra alloying elements as well that give it these properties?
We have added silicon in particular to stop the growth of detrimental crystals. So there are some crystals which are bad for toughness, and one of those is an iron carbide. And if we add the right amount of silicon, then the formation of that iron carbide is suppressed.
So we think of steel, or at least I think of steel from a lay perspective as just being iron and carbon, but clearly it is more complicated than that. How many different elements go into Super Bainite?
Yes, so there's at least 10 different solutes that we add. So apart from silicon, we add molybdenum, because when we make the steel commercially, we can't control certain impurities, and molybdenum acts like a scavenger and gets those impurities and therefore stops them from doing harm to the steel. We've got chromium and manganese to stop other reactions which happen at high temperatures. So it's a very carefully designed steel.
Centuries of bucket chemistry have gone into making better steels, but your technique has been somewhat more scientific.
Partly true. So what we do is we first start with calculations, go as far as we can, and then do the experiments to validate the calculations. If they're not correct, we go through that loop again. And that is a better way of doing it, because we develop the theory at the same time as reach our goal.
And speaking of the theory, what is it about having tiny crystals that gives it these properties? How does the crystal structure affect the final properties?
So if we pack a very large number of crystals inside the same volume, then you're presenting a lot of boundaries between crystals to any deformation. And the finer you make the crystals, the greater is the surface area between crystals in that given volume. So that makes it extremely difficult to deform. So super Bainite, for example, has a strength in which 1 square meter would be able to support the weight of 2.5 billion apples. So that's what we call 2.5 gigapascals of strength. And because the cooking process is so slow, we can make the steel in very large dimensions and very large quantities. So it's already been manufactured in thousands of tons.
We have spoken to people from Rolls-Royce before on the show who have talked about how they make jet engine blades, for example, by actually just forming them from one single crystal. Now, that obviously has none of these grain boundaries, but again, that performs a fantastic task for them inside a jet engine. Is it a trade-off, therefore? Does having grain boundaries offer one thing and having no grain boundaries offer something else?
Grain boundaries are very good for obtaining strength at room temperature, or say 200 or 300 degrees centigrade. But as you go above 500 degrees centigrade, there's a bit of space inside grain boundaries, which is not inside the crystal. So atoms can move about very easily in the boundaries. What that means is that if you're operating a turbine blade at 1400 degrees centigrade, it gets longer and longer and longer. So in that scenario, you really don't want any boundaries between crystals, and it's better to make the blade from a single crystal.
So you have these incredibly small crystals that give you all of this huge surface area of boundary. That gives you these unique, phenomenal properties. How do you see super Bainite really being deployed? Where do you think it's going to be most useful?
So I'll tell you both the good points and the bad points. The good points are that we can make this large in all 3 dimensions with an incredibly simple heat treatment, and the steel itself is quite cheap to make. So in any application where we require a combination of strength and toughness, this is perfect. So for example, for shafts, for armor, and for bearings, which Alan will talk about, the weakness is that because it is so strong, it cannot be welded. So I could not make a bridge out of it, for example. Large structures really need to be joined at some point, and this material cannot be welded at the moment. We are trying very hard to do research which will discover a method of joining it without disrupting the fine scale of the crystals. We haven't found it yet, but this is science, right?
It is, and I get the impression from the little I do know about the way that we do join metals that actually there's at least another hour of discussion just in talking about how to join 2 pieces of metal together.
Absolutely.
Well, thank you ever so much, Harry. That's Professor Harry Badisha from Cambridge University. Now, new materials are always needed to perform specific jobs, and even the tiniest improvement in properties can mean the difference between an engineering success and an engineering failure, or it can make a previously expensive project economically viable. We are joined now by Dr. Alan Begg from the Swedish company SKF. Now, Alan, presumably you rely on these sorts of step improvements all the time to make projects better, to make new products, and to remain competitive.
Absolutely. SKF is the world's largest bearings company. We've been established for over 100 years now. We were established on the back of an innovation when our founder invented what's called the self-aligning ball bearing. And SKF has led all of the developments, or most of the big developments in the bearings industry ever since. Use bearings from the tiniest things that go around to the very biggest. So, dental drills or disk drives in computers have bearings, right up to windmills, I guess, are topical at the moment. I think our latest bearings for the new big windmills that are being developed are nearly 4 meters in diameter.
Wow. Now, when I think of bearings, well, really, I think of the constituents of my bike that I occasionally have to get replaced or have to grease up. And those seem to basically just be tiny steel balls. What properties do you actually need in a metal that's going into a bearing?
Well, the steel balls are how most people think of bearings. Actually, and although SKF's name is associated with steel balls, we don't actually make our own steel balls anymore. They're pretty much commodity materials. The clever bit of a bearing are actually the two rings, the inner and the outer raceways that the balls rotate in. And basically any bearing is a set of rolling elements separating those two inner and outer rings, rotating to allow the inner and outer rings to rotate as freely as possible. The raceways, the inner and outer rings, the surface where the rolling element touches the raceway can be incredibly highly loaded. I was a metallurgist myself once. I actually studied metallurgy here at Cambridge. And I remember being told then that steel was getting pretty close to its theoretical strength. That the theoretical strength of steel, if you calculate it just in terms of the strength of a bond, is about 20 gigapascals. And I was told when I was studying materials science here in Cambridge that we were getting to about 10% of that strength. As long as you did it in thin steel wire ropes, you could get to about 2 gigapascals. I now look at bearings, and bearings, 2 gigapascal load's nothing. In fact, the compressive stress that's put on a bearing at the point of contact where a ball touches the ring, routinely it's about 4 gigapascals. And in extreme conditions, it can be getting close to 8 gigapascals. Not for very long times, but it'll stand it for a little while.
So what's changed? Why has the future that we saw a few years ago turned out so differently?
Well, people like Harry have been developing wonderful new grades of steel. I'd really like to give credit to Harry, because when I joined SKF about 5 years ago, and I was quite surprised how much we relied on steel and how little work was going on across the world to really generate new performances in steel. And that's one reason why I really wanted to set up a major cooperation with Cambridge University and with Harry. And SKF has set up what we call the University Technology Centre in Cambridge to exploit, amongst other things, superbainitic steels, but to also build our fundamental understanding of what really happens within a steel at that critical point of contact. And we have other university technology centres, another one in the UK with Imperial College in London, on what we call tribology. That's the study of the point of contact, really, the friction, wear and lubrication at that point of contact. We have some university centres in Sweden as well, right up in the north of Sweden, in Luleå, on condition monitoring, because we provide sensors and things with our more expensive bearings to actually tell you what's going on within them and start predicting potential problems that are going to arise either within the bearing or in the rotating equipment around the bearing. We've always sort of described the bearing as being at the heart of any rotating plant. By adding condition monitoring, you can think of it as the brain as well.
And going back to today's topic of superbainite, what is it about superbainite? What is it about these properties that makes it so attractive for you?
What we need in a steel is what's called fatigue resistance. A bearing, that rolling element rolls round and round and round. So if you imagine any element on the ring underneath that point of contact, it's continually getting stressed and then relaxed and stressed and relaxed over and over again. And when you do that to a piece of metal, you get what's called fatigue damage. Under this compressive load, you get what's called rolling contact fatigue damage. And that's quite a difficult thing to prevent happening. That's the way the bearing's loaded. And we've looked at many, many different microstructures created in many, many different ways. And superbainite seems to us to be the first real step change in thinking in steel for a very long time. Will it give us all we want? I don't know. We're still very much at the stages of examining it. Are there still some interesting challenges? Yes, I think there are. One of them is that the structure has some slightly unstable nature about it. There's some of the high temperature form of steel left in between those very, very fine nanoscale structural parts. And if that transforms during loading, it actually leads to a slight increase in volume. Now, the intriguing bit is, first of all, will it happen? But if it does happen, could this growth, could this expansion actually compensate for wear? Could we make a material that as it wears down, it grows up and compensates in some way for the wear? So there's all sorts of intriguing science still to be done in Super Bainite. But as I say, as a material, it's got the right kind of hardness, strength and toughness that we're looking for in a bearing steel. And so we're very interested to see if we can exploit its properties to make stronger, better bearings for our customers.
Fantastic. Well, thank you ever so much. That's Alan Begg from SKF. There's lots more still to come, so get your questions in by tweeting at Naked Scientists or commenting at facebook.com/The Naked Scientists.
From protons to photons and gluons to muons, The Naked Scientists. Science that's fundamentally more fun. For more information, look us up online at nakedscientists.com.
You're listening to The Naked Scientists with me, Ben Valsler. Very soon we will return to our topic of super strong steels to find out why they make incredibly good armour. And actually, if you punch holes in them, their armour gets even better. But now I'm joined by Chris Smith for a roundup of this week's science news. Sufferers of cystic fibrosis, or CF, have a lower pH in their airways, and this impairs their ability to kill bacteria, which ultimately leads to increased infections, inflammation, and damage to lung tissue. CF is a genetic condition caused by mutations in the cystic fibrosis transmembrane conductance regulator, or CFTR gene. The CFTR protein regulates the movement of ions across membranes, including the lining of the lungs, and when it fails, it leads to the build-up of very thick, viscous mucus. People with cystic fibrosis are especially vulnerable to lung infections, and until now it's not been clear how CF actually impairs the ability of the immune system to tackle infection. So writing in the journal Nature, Joseph Zabner and colleagues at the University of Iowa immobilized Staphylococcus aureus bacteria on solid grids of gold and placed these on the lung surface of both healthy and pigs with cystic fibrosis. Even a brief exposure to healthy lung tissue killed the bacteria, but only half as many were killed in the CF lungs. The airway surface liquid, or ASL, from cystic fibrosis pigs consistently killed fewer bacteria than that from their healthy littermates. Now that proved to us that airway surface liquid itself is capable of rapidly killing bacteria, and it proves that the effect was impaired in cystic fibrosis. Now, there were no obvious differences in the abundance of antimicrobial proteins in the different liquids, so the researchers concluded that it must have been some other chemical factor that was having that effect. And as the CFTR protein is linked with secretion of hydrogen carbonate, that's HCO3-, and that's an ion important in pH buffering, they decided that they would investigate the effect of pH. And they found that both in vivo and in vitro, CF lung fluids showed a lower pH. When they raised the pH of these lung fluids, it restored the ability to kill bacteria. So this is a simple and elegant study that suggests that correcting lung fluid pH could really help to prevent infection taking hold in the lungs of cystic fibrosis patients. And it could be achieved by something as simple as a bicarbonate aerosol.
Is it relatively easy to correct the pH? So if you had someone who had cystic fibrosis and you wanted to render their airways a bit more alkali with bicarbonate or something to compensate for this, is that quite easy to do?
Well, they certainly have been doing it in the cystic fibrosis pigs, and they found that it definitely does work in the lung. But how you then take that a step forward and say, well, we can now deploy this into people is slightly different, because it may be that an alkaline inhaler, as it were, is actually damaging, and it may be that actually working out the balance is quite difficult. So it looks like it should be very simple in theory, but I think they are being quite careful to say that we can't now just straight away go out and do this. It still needs a lot of research before we can actually make it into a medical use.
Now, here's another interesting story this week. Unblocking blood vessels. Now, about 1 person in 3 is destined to develop some kind of heart problem in their lifetime. The commonest heart problem being an MI, or myocardial infarction, a heart attack. And this occurs when a blood vessel becomes obstructed, usually with a blood clot or a thrombus, which has occurred on a damaged area of the blood vessel wall, and either blocks the vessel there in situ or breaks away, floats downstream, and then blocks the vessel at a point where the blood clot is bigger than the vessel lumen. And you then deprive the tissue supplied by that vessel of blood and therefore oxygen and sugar, and the tissue can die. And that's what happens during a heart attack. Now, one way to manage that problem is that doctors can inject a chemical. There are two that are available. One is called streptokinase. It's made by the Streptococcus bacterium. The other is called TPA, tissue plasminogen activator, and this is a natural human protein. And in both cases, they break down clotted blood. So you can inject these chemicals into the bloodstream. They will go to the obstruction and they will dissolve the clot, thereby restoring blood flow to the damaged area. Now, the problem is that doctors have to give very big doses of these agents, and they are delivered to all the tissues in the body, which means that if there is a thrombus or an area of a blood vessel that's been damaged that you do want to stay sealed because, for instance, you had a small rupture in a blood vessel in your gut, for example, and you give one of these drugs, there is a risk that then you dissolve the protective thrombus and you cause hemorrhage somewhere else. And this can also occur in the brain. There's a risk of getting a stroke after you treat an obstructed blood vessel in this way. So if there were a way to target this clot-dissolving therapy more precisely to where it needs to go, then that would be a terrific step forward. And this week, publishing in the journal Science, there is an announcement of an approach that the researchers who are at Harvard, this is Donald Ingber and his colleagues, they dub this SANTS, S-A-N-T-S, Shear Activated Nanotherapeutics. Now, put simply, what they've done is they take a chemical called polylactic co-glycolic acid, PLGA, and they spray a fine mist of this chemical, and the droplets dry out, and they form tiny aggregations about 1 micron or 1,000th of a millimetre across, which are themselves composed of lots of tiny nanoparticles all glued together. And they have found that these particles, because they are water-hating or hydrophobic, they cling together. And if you inject them into the bloodstream, under normal flow characteristics, they stay sticking together. But in areas where blood vessels have been narrowed because they are blocked or partially blocked by a thrombus, you get turbulence or shear forces in the blood vessel. And that turbulence is enough to disrupt and blow apart these aggregations. So what the researchers have been able to do is to stick onto these aggregations molecules of tissue plasminogen activator, the clot-busting drug. In fact, they stuck about 500,000 molecules on each of these tiny particles. They were then able to inject those into the bloodstreams of mice that had blood clots, either blocking their blood vessels in their guts or their blood vessels in their lungs, and they could dissolve out the clots using this technique, and they didn't see any bleeding anywhere else. So this looks like you've got a way of exploiting the fact that in the region where blood vessels are blocked, you get more turbulence, and the turbulence can cause these particles to break apart and then deploy their drug-active content only where it's needed and not where it's not needed.
And is it only regions next to clots where you get these shear forces, where you get this turbulence in the blood? Are there not other parts of the circulation where blood is just turbulent as a result of the actual layout of the veins, for example?
They've looked at that. In fact, they do some models and they also do modelling in vivo. And what they found is that it's only in regions where you have vessels obstructed or almost 90% occluded that you get the level of turbulence and therefore shear forces that you need to disaggregate or break apart these drug-bearing nanoparticles. In fact, in regions where there are 90% or more occlusions of blood vessels, then the level of shear forces is between 10 and 100 times greater than anywhere else that you would see in the body. So this is a really neat way, actually, of targeting the therapy, because that range between what's normal and what occurs in the disease state is so wide that you can be selective for one and not the other.
Very interesting stuff. And now from disappearing blood clots to disappearing dust. A huge, hot, dusty disk around a sun-like star seems to have vanished before our very eyes, but its disappearance cannot be explained by any current scientific theory. The star TYC 82412652-1, one of those wonderfully grabby star names, has been observed by a number of different telescopes, and a bright infrared glow indicated the presence of a very large amount of warm dust that was absorbing visible light from the star and then re-emitting it in the infrared range. Carl Mellis and colleagues at the University of California, San Diego, report in Nature that this dust seemed to be the result of the collisions of rocky objects, and it actually fell in the region analogous to where rocky planets formed in our own solar system. Estimation of the size of the dust grains hinted that it could be a system undergoing an active stage of terrestrial planet formation. So this made it an ideal candidate for future observation because our theories of planetary formation suggest that rocky planets just like the Earth will eventually form from these disks of dust and ice. But since 2008, the infrared emission from this star has reduced by a factor of about 30, suggesting that the star is now only host to a meagre amount of far cooler dust. Now, this is an unprecedented observation. Changes like this have never been seen or even predicted before, so we don't know what could have caused it. We've seen that no major changes have occurred in the star over this time, so it's very unlikely that a violent stellar event just blew all the dust away. Models of planet formation predict that you would see a loss of dust, but it would take many thousands of years, as the gravitational field of these newly formed planets would disturb the dust cloud. Now, Mellis and his colleagues argued that only two hypotheses could actually fit the results, and they're one called the collisional avalanche hypothesis, where dust grains gradually become smaller through banging into each other until they're below a certain threshold, and then they get blown out of the system by radiation pressure from the star itself. The other hypothesis is called runaway accretion, and this is where gas that exists in the cloud places a sort of aerodynamic drag on all of the dust. That causes it to slow down and fall into the star. But both of these ideas have problems. We don't see evidence for all of the gas, and the collisional hypothesis should take a lot longer than it has done. So the jury is still out. So even though we lack a clear explanation for what actually happened, it's a unique observation, very exciting, and certain to push our understanding of how planets like the Earth originally formed.
Incredible. Well, also this week, a unique and explosive demonstration took place at Cambridge University. Explosives play a huge role in our lives, from mining the materials that make computers and cars, through to excavating tunnels and even controlling avalanches, and of course lighting up the skies for nice firework displays. Professor Chris Bishop, who's Chief Research Scientist at Microsoft Research in Cambridge, wanted to highlight the science and technology in explosives rather than just gratuitously blowing things up, and that included both humble gunpowder and also modern high explosives, and he found a clever new way to show them all off in a talk that he gave earlier this week.
Black powder is really just a mixture. It's a mixture of charcoal, sulphur and so-called saltpeter or potassium nitrate. And it works because the saltpeter, the potassium nitrate, acts as a very concentrated source of oxygen. So the carbon in the charcoal and the sulphur, instead of burning in the oxygen from the air, they burn in the built-in oxygen in the potassium nitrate. And so it's a much more concentrated form of oxygen, therefore a much more concentrated and intense combustion.
So if I light it, what happens? Does it immediately go bang?
Not quite. What happens is that the ingredients first of all have to melt so that the molecules can come into contact with each other. The potassium nitrate has to start to decompose, so it needs a certain amount of heat to get it going, and then the chemical reactions can take place. And they're essentially reactions of burning, so the carbon in the charcoal will burn with oxygen from the potassium nitrate to make carbon dioxide and release energy, for example. And we can try it here if you like. I've got 1.5 grams of a good quality commercial gunpowder, and we'll see what happens when I just light a pile of this gunpowder in the open.
Lots of smoke, but it wasn't a bang.
No bang. So what we had there was a very, very rapid burning. The technical term we give that is deflagration, but it just means burning. What's happening is, imagine a trail of gunpowder and setting fire to one end. As the gunpowder at one end burns, it generates heat, and that heat raises the temperature of the bit of gunpowder next to it in the trail. When that gets hot enough, that in turn will combust. And so it's a process of propagation involving the transfer of heat. So it's a relatively slow process. In that case, there's no explosion at all. If we actually want to get a bang, if we want to get a proper explosion, we need to speed things up. And
so when Guy Fawkes shoved tons of gunpowder under the Houses of Parliament hoping to blow it up, would that not have worked then? Because it was just a pile of gunpowder, rather like you had there.
Well, of course, it was in a cellar and surrounded by very thick stone walls, so it would have been very well confined. So I think there's little doubt that it would have resulted in an enormous explosion and the complete destruction of the House of Lords, yes.
So is that how explosives involving gunpowder actually work then? You confine the explosion?
That's right. So if you're listening to a fireworks display and you're listening to all the bangs, it will be gunpowder or another type of low explosive that's been confined in order to produce the bang. Again, we can sort of illustrate that here because I've got another sample. It's again 1.5 grams of gunpowder. It's exactly the same type as before, but this time I've put it into a cardboard tube and bound it up very tightly with tape, so it's very strongly confined. And what we'll do is we'll set this off using a little electrical igniter that's buried inside the gunpowder.
I should put on some ear defenders.
Okay, we're ready? Here we go.
Okay, my ears are ringing even though I had the ear defenders on. So that was exactly the same amount of gunpowder as we lit that went puff before, but that's the power of confinement. You get that huge bang.
That's right, that's dramatically different. But it's still a very rapid burning. So what's happening is that as the gunpowder starts to burn, it releases energy in the form of heat. But that heat is now trapped, it can't just escape. And so the temperature rises, and chemical reactions go faster at higher temperature. So as the temperature increases, the rate of reaction increases, and so the rate of heat production increases, which in turn raises the temperature. We have this sort of positive feedback loop leading to a kind of runaway reaction, which results in this explosion. For many years, for perhaps 1,000 years, that was really the only kind of explosive that people had. And then sometime around the middle of the 19th century, people began to discover new kinds of explosives, so-called high explosives.
Fundamentally, why are they different to gunpowder?
The key difference is the way in which they are initiated. So gunpowder undergoes this very rapid burning. Now, a high explosive, something like nitroglycerine or TNT, decomposes by a process called detonation, which is a very different physical process, and it's very much faster and very much more powerful. Because the oxygen, if you like, is built into the same molecule. So in a molecule of, let's say, nitroglycerine, you have the carbon and the hydrogen, but you also have the oxygen and the nitrogen. That's the most perfect mix you can have between the fuel and the oxygen. The carbon can combine very readily with the oxygen to make carbon dioxide. The hydrogen can combine with oxygen to make water. The nitrogen is left over. Now, nitrogen occurs in a lot of explosives. It's very important because the nitrogen gas in the air consists of molecules containing two atoms joined together by one of the strongest bonds in chemistry. So if two atoms of nitrogen get together to make a molecule, they release a lot of energy. And that's one of the reasons why high explosives release so much energy.
But when we want to make it blow up, what do you need to do for that?
So what we need to do then is to send in a very fast shockwave in order to get the explosive to detonate. So a detonation is where a shockwave is travelling through the explosive very much faster than the speed of sound. So this modern high explosive would detonate at a speed of about 8,000 metres per second.
Gosh, so that shockwave is putting energy into the chemical bonds in the mixture, breaking some of them and making others recombine, which then makes a bigger shockwave, which then goes on to the next bit of the molecule, and you get a sort of explosive domino effect, for want of a better expression.
Yes, exactly right. It's the energy released by the high explosive which sustains that shockwave. If you send a supersonic shockwave into a block of material, it would rapidly slow down to the speed of sound. But if the material is at high explosive, because it's detonating and releasing energy, that energy just behind the shock front is sustaining the shock front and keeping it going at that supersonic speed. So one of the things I really wanted to do in the lecture is to try to give people a sort of visceral feeling for just how fast a detonation occurs. So I came up with the idea of using something called shock tubing. So I've got some shock tubing here, and it looks just like a piece of yellow plastic tubing, 3 millimetres across. It's got a 1 millimetre diameter hole down the middle. And inside it contains a very light dusting of a high explosive called HMX. This is one of the most powerful explosives known. And what I can do now is to demonstrate a shockwave travelling down the tube.
So this little piece of plastic tube is about 20 centimetres. What are you going to use to detonate it?
What I'm doing is I'm plugging it into an initiator, which is essentially an electrical device. It has a couple of buttons. I press the first button, which will charge up a capacitor. When I press the second button, it will produce a spark, and that's enough to initiate this shockwave.
I certainly didn't miss that. Yes, and you can see the flash go down the tube.
That's right. But of course, at such a high speed, it appears to be essentially instantaneous. So what we'll be doing in the lecture is to use 0.5 kilometre of shock tubing, and this is being wound, as you see, around the walls of the lecture theatre. So it'll go around the audience 4 or 5 times, and then what we're doing is to initiate one end of the shock tubing, and about 1/4 of a second later, the shockwave will arrive at the other end. What I'm hoping is the audience will actually be able to perceive the delay between the start of the shockwave and the end of the shockwave, and might even be able to see this pulse of light racing around their head several times.
Has anyone ever tried to blow up a lecture theatre in this way in the past?
I'm certainly hoping not to blow up the lecture theatre, but I think it's the first time, as far as I know, that somebody's tried to use this sort of method to illustrate the speed of detonation as a live demonstration in a lecture theatre.
And I'm pleased to say it definitely worked. People reported seeing the explosion whirl around their heads. So well done to Professor Chris Bishop with a first-of-its-kind demonstration surrounding the audience with high explosives.
And it has been a big bang week for science as well, with researchers from the LHC reporting the discovery of a Higgs-like particle. To find out more about what they've discovered and what it means for us, here's Mira Senthilingam with the Naked Scientist Newsflash.
This week saw scientists at CERN announce the discovery of a Higgs boson-like particle at the Large Hadron Collider, or LHC. The existence of the Higgs boson has long been part of the so-called standard model of particle physics, but until now its existence wasn't confirmed. CERN Director General Rolf Hoyer.
We have discovered a new particle, a boson, most probably a Higgs boson, but we have to find out which kind of Higgs boson this is. What are its properties and where do they point to? But at least we know now that we can soon close part of the chapter of the standard model. We have now found the last missing cornerstone of it. It's the beginning of a long journey to investigate all the properties.
The discovery answers a long-standing question regarding why some of the fundamental particles in the universe, like protons and neutrons, and the quarks, leptons and bosons that make them up, actually have mass. The boson was detected by the CMS and ATLAS experiments based at the LHC. Professor Joe Incandela is from the CMS experiment.
This boson is a very profound thing that we found. Okay, this is not like other ordinary particles. It really is. We're reaching into the fabric of the universe at a level we've never done before, and we're on the frontier now. We're on the edge of a new exploration.
Without the presence of Higgs bosons, located within the Higgs field which permeates space, subatomic particles such as quarks and leptons would simply move in all directions at great speed, rather than clump together to form matter. In their search, scientists collided billions of protons every second to release large amounts of energy within which the elusive Higgs boson could form. Only a small percentage of these collisions led to the formation of these bosons, which then decay rapidly into photons. By studying these photons, the CERN scientists have been able to deduce the presence of a new fundamental particle, as Professor Jordan Nash, head of high-energy physics at Imperial College London, explains.
So the two cleanest ways in which we've seen it and which have our most statistical significance are the events where it produces just two very high-energy photons. So these are just two particles of light which smash into our detector very cleanly, and the Higgs boson always produces them with exactly its mass. So by looking at these very, very clean signatures, we can spot it. It's very, very rare indeed to have such a clean signature, but it's one where when you get it, you have a quite high certainty that you've actually produced a real particle.
The teams detected particles with energy levels indicating a mass of 125 to 126 giga-electron volts, or 133 times heavier than a proton. The findings build on preliminary results hinting at the presence of a Higgs-like particle that were announced back in December 2011. But now the CERN teams have identified the presence of this particle with more than 99.99994% certainty, a level known as 5 sigma.
5 sigma it's a measurement of how statistically confident we are in our measurement being consistent with a signal as opposed to a background. And so sigma is a measurement of the relative confidence, and it comes from a probability distribution where you can have 1 sigma, which is says you have about a 1/3 chance of having confused your signal with the background. 3 sigma says you have about a 1 part in 1,000 chance of doing that, and 5 sigma says you have less than 1 part of a million confusing a signal with background.
This confirmation would revolutionize the world of fundamental physics as well as our own. Dr. Emily Nurse from University College London is part of the Atlas project.
It's a very fundamental finding for our understanding of the universe. It's very difficult for us to say what it could possibly lead to. All we can say is that we know that our modern world has completely relied on the previous generations doing fundamental research. For example, computers, television, like all the sort of medical equipment that we use, MRI scans, all of these things, they've all come from understanding the universe better at a fundamental level, and that just eventually then leads on to technology as you sort of trickle down the line.
Confirming the Higgs boson's existence would help scientists recreate what happened just after the Big Bang. In fact, 1/10 of a second after the event, in which massless particles gained their mass from the Higgs field to form atoms, ultimately leading to the universe we see today.
Mira Senthilingam with a special Higgs boson newsflash. And to explain more about the discovery itself, we've produced a special edition of The Naked Scientist scrapbook. You can find that on our homepage and at thenakedscientists.com/scrapbook. And if you'd like to read more about any of the stories we've covered this week, the transcripts and references can be found on our website at thenakedscientists.com/news. Now, nanotechnology promises to make smelly socks a thing of the past, and we've already heard today how it could revolutionise medicine and the drugs industry. But what are the environmental dangers of these tiny particles? A joint research project between the UK and United States has been set up to analyse the potential risks of nanomaterials. One of the studies is being led by Teresa Fernandez at Heriot-Watt University in Edinburgh. Planet Earth podcast presenter Richard Hollingham went to visit her in her lab.
We have here a range of projects looking at hazards. So we keep some organisms, very, very small organisms. We keep some primary producers, some algae, microalgae, single-cell organisms. And we keep the water flea, for example, and some worms, some aquatic worms.
Can we have a look at some there?
Sure.
And these look like just large freezers, really? Food freezers, fridge freezers.
You could nearly walk into these ones.
So you've got these beakers, a couple of litre sort of beakers with slightly greenish water and these little water fleas skimming around. And then in there you've also put some nanoparticles, nanomaterials to see what happens.
If they indicate that there are reasons to be concerned, for example, there's mortality or reduced reproduction or other endpoints we might be looking at, then there's a concern. And if these effects happen at low concentration, there's a concern that there might be, a reason to prevent or I don't know, have controls in use of these chemicals.
Now, Teresa, while you're looking at the environmental impact of these nanomaterials, I'm also with Helena Johnston, and you're looking at the impact on human health.
So in order to do that, we can either look at the effects on cells cultured in vitro, or we can look at the effects within animals in vivo.
So when you say in vitro, you mean in the test tube?
Yeah, so in a cultured conditions in a test tube. So what we generally do is we take cells isolated from different parts of the body. So you might get exposed via inhalation, so the lung would be a target, via ingestion, so we have the gut as a route of exposure, via the skin. Once the nanoparticles get exposed to these different exposure sites, they can access the blood because of their small size and then travel throughout the body. So the liver is a primary target. We also look at the kidneys, the cardiovascular system, the kind of list is endless.
Teresa has chambers full of water fleas and the like. Mm-hmm. You have some human cells.
Yep, so the cells need to be cultured at 37 degrees Celsius because that's what you would
Our
have.
body temperature.
Yep, exactly, body temperature. They need a supply of carbon dioxide and oxygen, and they need a medium which gives them all the nutrients they need to grow in these sort of artificial conditions.
So
we've got
open the cabinet up.
Cell types in here. So for example, this is an epithelial cell, so it's found within the lining of the lung. So
it just looks like a clear liquid, or a slightly opaque
So if you look
liquid.
at the back of the dish, you can see the cells growing.
Oh, okay,
so all
yes,
these little kind of islands, if you like, are the cells.
So they're the same
attaching.
cells that we'd have in our lungs?
Yes. So these have been isolated, I think, from a tumour. So these cells will grow indefinitely in culture. If you take them from a human, they'll only divide a certain number of times, and it limits the amount of times you can use these cells.
You've got some darker ones in here as well.
So these are macrophage cells, so an immune cell within the body, so they're responsible for clearing foreign materials. Again, you can see them growing on the back of the dish, and whereas these epithelial cells will all grow together, These ones are isolated.
And when you're looking at these, again, you're looking for the impact of nanomaterials on them.
Types of toxicity tests we do will administer the nanoparticles and see if the cells die, so they have a cytotoxic effect. Do they elicit an inflammation, oxidative stress? So these are all common mechanisms that we know nanoparticles can act, and it allows us to compare the toxicity of different types of nanoparticles and see if they elicit a similar toxicity or some are more potent than others.
And Teresa, doesn't this come to the nub of this? That these things are already out there. Shouldn't maybe this work have been done 10 years ago when these kinds of products were being developed?
Industry can develop very fast, and the research and evidence needs to take its time, because you don't want necessarily to prevent an area of industry that has great promise for society. So it's a question of getting the pace right, speed up the research, speed up the ability to translate results from research into the regulatory process.
Teresa Fernandez and Eleanor Johnston from Heriot-Watt University in Edinburgh, talking to Planet Earth podcast presenter Richard Hollingham. You can find more Planet Earth material on our website at thenakedscientist.com/Planet Earth.
Bringing the facts to bear. The Naked Scientists.
You're listening to The Naked Scientists with me, Ben Valsler. This week we're looking at a new super strong steel called Super Bainite. Another potential application for a very strong metal is in armour, protecting people and vehicles from threats like bullets and bombs. At the Defence Science and Technology Laboratory, or DSTL, in Porton Down, researchers including Professor Peter Brown work on finding the right balance of material properties for the perfect armour.
People have been looking for good armours for centuries. And the trouble with armour is that as soon as you create a good one, somebody creates a bigger, a better weapon to defeat it. So there's no end point that you get to and go, aha, that's the perfect armour. The other thing I always find quite intimidating about armour is you're up against Leonardo da Vinci, because he invented the bullet. And in terms of opposition, a Da Vinci design is not easy to defeat. You'd be dead 500 years and still causing trouble. And because the rules keep changing, as soon as you feel as though you've got a grasp on what you might need for an armour, the threat changes and all those rules go out the window. Generally speaking, it should be hard. We find the best high-performance armour steels are also hard. And the very, very best armours that provide the highest levels of protection are ceramics. And they're unbelievably hard. But you would have then thought that something like toughness is a good thing. If you're going to give your armour a whacking great clout from a fast-moving projectile, something that's tough, common sense would tell you is a good idea. But you look at ceramics and they're as brittle as anything. You drop a ceramic plate and it'll shatter. So common sense would tell you toughness is a good thing. So you start using common sense to help you out in armour design, you probably become a cropper quite quickly.
I assume there can't just be a one-size-fits-all armour as well. If you are putting something on the outside of an armoured vehicle, that must be very different to the body armour that a soldier would wear.
That's the trouble, that an armour that's good for one threat, say armour-piercing 7.62 ammunition, that solution probably won't work for your improvised explosive devices. So not only is the armour properties dependent on a whole range of properties, it's also dependent on what the threat coming in is as well. And that gets you to the point of trying to understand what happens at the ballistic event. As the threat, the projectile, whatever it might be, hits your armour, whatever that might be, that moment of impact is an unbelievably violent event. Any sensor you put in there, by definition, is destroyed as the bullet hits it. So it's a really very difficult event to get to. We're getting closer and closer with modern characterization techniques, but we're not there yet. And until we actually understand the ballistic event itself, I think we're going to struggle to design armours in the sense that buildings are designed. That's thoroughly understood, and if you design a structure or a building and the computer says yes, you don't build a model, you just go and build a building. Materials modelling is not at that stage yet.
How do you test a material? Presumably you are just simulating these impacts by actually firing projectiles at a block of material.
Yep, absolutely right. There's no substitute for putting it on the range and shooting at it. Because at the end of the day, you're asking people to put their lives on this technology.
So how did you come to be testing Super Bainite as a potential armour?
Well, it's a steel. That's a good start. The thing about steel, as a general comment, is that it's often the solution to several questions in one material without that much change in its composition or processing. So in terms of how well Super Bainite performs, bearing in mind that most things have no usable ballistic properties, Super Bainite is right up there with the very best armour steels that have ever been invented. And I think, to be honest, armour steels for the foreseeable future are probably at their limit of ballistic performance. But yeah, Super Bainite, no better than the best, but as good as the very best. And that, trust me, that's saying something.
So how do you now see this being deployed? Is this going into body armour, or is this going to line the next generation of armoured cars? Where do you see Super Bainite turning up?
The principal application will be for the protection of land vehicles, armoured fighting vehicles that go on the battlefield through to diplomatic limousines. It has commercial uses as well. You can use it for steel toe caps and hacksaw blades. You can keep producing Super Bainite for non-defence applications day in, day out, and you can just sell as much of that stuff as you can make. And then when there's a defence requirement, you just put in an order. The standard Super Bainite composition is slightly tweaked for defence applications. And that's where partnering with an industrial company has proved very useful. Not only do you get, are they prepared to make the alloy, they're prepared to make it in a range of different product types. You can buy it in as solid plate, or you can buy it as perforated plate, which has an array of holes in it that reduce the weight and increase the ballistic performance. Although that's traditionally putting holes in the armour is the enemy's job, it turns out that if you do it right, it's now our job.
Why would putting holes in armour make it better?
Yeah, so if you're feeling confused at this point, join the rest of the world. That is an entirely rational and common sense based feeling, but I've warned about the use of common sense earlier on, that in fact we're not putting holes into the armour, what we're putting in is edges. And if you say drill out half the steel and replace it with holes or fresh air, the bullet will always land near an edge, and the material will fail in an uneven way and cause the bullet to topple over, and it stops becoming a fast-moving, sharpened projectile pointed in the right direction, turns into a blunt, toppling fragment. That's still got a lot of energy, but at least the sharp, pointy bit isn't heading in your direction anymore. We've got means of energy absorption, and that toppling mechanism is a way of defeating the sharpened projectile concept that Da Vinci originally came up with. The thing about holes is, if they're too big, then all the bullets just go through the holes. So there is a ratio of hole size to threat size, and if you've got a big threat, you need bigger holes. But that means that the smaller threats, which are still very dangerous, can get through. So what you have to move towards is away from a circular hole to a slot. That's quite narrow, but it still has the same amount of edge length. And that slotted, perforated design is the one that we're probably going to go forward with and commercially exploit fairly shortly.
Professor Peter Brown explaining why you should throw common sense out of the window and trust that holy Super Bainite will make good armour. And this is The Naked Scientists with me, Ben Valsler. I'm joined by Professor Harry Padiccia from Cambridge University and Dr. Alan Begg from SKF. There's just time for a few of your questions, including this one from Peter Gemley at Twitter. He asks what the crystal structure of Super Bainite actually is.
Yeah, there's actually two kinds of crystals. One in which the atoms are arranged at the corners of a cube and a single atom in the center of the cube. So we call that body-centered cubic. And the other one where you still have the atoms at the corners of a cube, but also at the centers of the faces, and that's a face-centered cubic crystal structure.
So that would be like looking at a die where every surface just has a 1. So it's impossible to roll a 6 because they're all just 1s.
Correct.
And what is it about those structures that give it the properties?
Yeah. The body-centred one is very strong, but is not as tough as the face-centred cubic. So if you combine them, then you have the ability to absorb energy as well as be strong.
And so what is it that actually causes these structures to form when you've got it in your pizza oven for however long?
Right. First we go to 1,000 degrees centigrade where everything is face-centred cubic. And at 200 degrees centigrade, the body-centred cubic form is favoured. So it grows inside the face-centred cubic form.
And that leads us on to a question from Raheem Campbell, who asked how environmentally friendly this new type is. Alan, if you have to do such a long heat treatment for it, presumably it burns off a lot of energy.
The immediate reaction from all our commercial people was, "Oh my goodness, that's never going to work. We can't tie things up in a pizza oven or in a furnace for 2 weeks." We do some extended heat treatments, but most of our heat treatments would be less than a day. But Harry's point of you do all this at pizza oven temperatures is an interesting one. Normally you heat treat much higher temperatures than that, and both the cost of a pizza oven is relatively low and the heat loss at that temperature is relatively low. So although you're holding things for a long period of time, the energy loss could actually be a lot less.
So obviously it needs quite a long period in order for that structure to evolve, but because it's so much lower temperature, it's altogether a more efficient process.
It could be, yeah.
Excellent. Well, thank you ever so much, both of you, for joining us. And now, picking up the right cutlery and dishing up delicious delicacies, here's Hannah Critchlow with our Question of the Week.
The Naked Scientist's Question of the Week, brought to you in association with the Houter Wisman Foundation, supporting science and education from Alpha to Omega.
In a quest for pleasure, we ask if our choice of cutlery alters our food's flavour.
Hello, Naked Scientists. My name is Fabian Weller, and I'm calling from Dubai. This is my dad's question. Does metallic cutlery really affect perception of food taste? Common wisdom tells that caviar should not be eaten from steel spoons, and for gourmet occasions, often porcelain or bone spoons are used. How much of this is a fancy myth?
Professor Mark Miadnovich from University College London sinks his teeth into this question.
Well, I've got some cereal here. I'm eating it with a silver spoon. I wasn't born with a silver spoon in my mouth, but I've since acquired some. There's a slight taste from the silver, as I expected, because we actually did some experiments making spoons of different materials: gold, silver, tin, copper, zinc, stainless steel, of course. And we did blind taste tests with just the spoon alone, and found that people are very sensitive to the different tastes of the different metals. In fact, can distinguish between them very clearly. They find them to be, to a greater or less extent, bitter, metallic, unpleasant is another adjective people use for some of these metallic tastes. And that, we found out in the end, was due to something called the electrode potential of the metal. So that its ability to react in the mouth and produce ions of a particular type. So in the case of a copper spoon, copper ions, and in the case of silver, silver ions. So the least reactive metals are the ones you'd expect to taste least, and that's broadly what we found.
So metals produce ions in your mouth, and the more reactive the metal, the stronger the taste produced. The alloy stainless steel actually produces the mildest taste. But do some foods taste better with different materials? Professor Zoe Laughlin from University College London led blind taste tests to find out.
Specifically something like a boiled egg, for example, where the sulphur really reacts, and a material like silver is a really bad idea because it tastes really foul, whereas gold is quite delicious. And then when it comes to sweet things, we actually found the strong taste of the copper and zinc actually made the sweetness of the food even stronger.
And beyond chemistry, what else can alter your perception of taste? Back to Mark Miadnovich.
The size of the spoon, the shape of the spoon, the thermal conductivity, in this case, it's conducting heat away from my tongue very quickly. It's cool. If I start using a plastic spoon now, we're into a whole different ballgame. And this is where this example of thinking about what spoon material you might use to eat caviar is quite an interesting one, because actually, even if the material is chemically inert, like something like ivory, there are subtle differences in the way that heat is taken from your tongue and your mouth. The texture is very important. So wooden spoons tend to give a particular sensation in the mouth, which can be both pleasant or unpleasant depending on who you are.
So your choice in cutlery will alter how you perceive your food to taste. Now let's move our questioning eyes down the digestive tract.
Hello, my name is Claus Goffeng. I'm from Gothenburg, Sweden. Much food-related illnesses come from contamination by intestinal bacteria due to poor hygiene in meal preparation. So the obvious question is, will the person whose bacteria got into the food be sick as well?
So, can your own bowel bugs make you sick? Or can they only make other people sick? Send your thoughts to chris@thenakedscientist.com, tweet @nakedscientists, write on our Facebook page, or join in the debate on our forum, which is at nakedscientist.com/forum.
Hannah Critchlow. And that's all we have time for this week. Please keep sending your questions and comments to chris@thenakedscientists.com. You can tweet @nakedscientists, or you can post them on our Facebook page. Next week, we try to satisfy your thirst for science as we answer your science questions. So if there's anything you'd like to know, then just get in touch. Many thanks to Harry Badishia, Alan Begg, Peter Brown and Chris Bishop, and also to our production team of Mira Senthalingam, Hannah Critchlow, Chris Smith and Will Nichols.
The Naked Scientists podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the STFC, the Natural Environment Research Council and UK FAST. For more cutting-edge science, join us online at nakedscientists.com.